today I'm going to show you what would happen if I had two chiral centers in my molecule. And if you look at the structure that I've shown you here, you will see that I've labeled my chiral carbons. And in each of these chiral carbons, you can see that there are four different groups around these chiral carbons. If you look at the first structure, you can see that I have a hydrogen, a chlorine, a methyl, and then this entire group. And if you look at this chiral carbon, I have a hydrogen, a hydroxy, a methyl, and then this entire group here, this carbon group. And I'm going to take these different groups and place them arbitrarily around these chiral carbons. And if you look at this particular structure, you will see that I've deliberately put the hydrogen atoms behind the plane of the board, the two methyl groups into the plane, with the chloro and the hydroxy group pointing out at me. We can see this a bit better in the molecule, and I'm holding one of the methyl groups in my hand, and you can see that's in the plane. The other methyl group pointing down is also here in the plane, and what you can see is that I have the two groups, the chloro group with the blue one and the OH group, the red one, pointing out at me, and you can see the two hydrogens on those central carbons, the hydrogen atom here and the hydrogen atom in the back there, both pointing away from me. So this is what the molecule looks like, and you can see that we can represent it by a perspective formula like this. So this is called a perspective formula, where I show the stereochemistry around each of the chiral carbons, both here and here. What I'm going to do now is take a mirror image of this particular molecule. And if I take a mirror image of this particular molecule, you'll see now that I have both my chiral centers in the molecule, and my carbon atom that you see here has the hydroxy group pointing toward me and the chlorine group pointing toward me, and then the two hydrogens pointing away from me, and the two methyl groups pointing up and down in the plane. And I can show you now a model to see that both of these are actually mirror images of each other. If you look at the structure here and the structure here, you can see that both the chloro groups point toward me, both the hydroxy groups point toward me, and the other two point away from me, the two hydrogens at the back, both there and there. Those hydrogens point away from me. So these two are mirror images of each other, and that's what I've drawn here, the two mirror images of each other. Now I'm going to try and convince myself that these are mirror images, because if they are mirror images which are enantiomers of each other, the chiral centers around each of those carbon atoms should change, which means that if I name them, the names should also change. So I'm going to use the same rules that I used previously to name these structures. And if I recall those rules, you will see that, I'm just going to focus a bit here, that the chlorine atom is priority group number 1, the carbon group is priority group number 2, and that's because of the oxygen attached to it. And you'll see that the carbon with the 3 hydrogens is priority group number 3 and the hydrogen 4. And then going from group 1 to group 2 to group 3 to group 4, group 1 to group 2 to group 3 would be in a clockwise direction, so this carbon would be R. And if I try to name this carbon center, you'd see I also go from priority group number 1, which is the hydroxy group, to the carbon group number 2, to the methyl group number 3 in a clockwise direction. So this carbon is also R. And I would expect that if I get an enantiomer of this, or a mirror image of this, that this carbon would change to S and this carbon would change to S. And that's exactly what happens. If I look at this particular molecule, you'll see now that if I label this priority group number 1, 2, and 3, I go in an anti-clockwise direction. So this carbon is S, and likewise here, chlorine is 1, this carbon group is 2, the methyl is 3, and I go in a anti-clockwise direction, which means that this carbon is S. So I've labeled this as 2R and 3R because carbon number 2 is the carbon with the hydroxy group and carbon number 3 is the carbon with the chlorine group. So always look at the hydroxy group first and then the carbon with the chloro group. And you can see the carbon with the hydroxy group has been labeled as R. And the carbon with the chlorine group has been labeled also as R in this case. Alright, you can just focus a bit here. And you can see I have a 2R, 3R isomer. And if I look to my to my right, I have a 2S, 3S isomer. Now I'm going to take this particular molecule and leave the stereochemistry around that center the same, but just change the stereochemistry around that center. And I can do that very easily just by swapping these two groups. So I'll put the hydrogen now in front and the hydroxy at the back, keeping this methyl group pointing to the top in the plane. And I can do that here. So what you'll see that I've done in this particular molecule that I've now labeled C is that I've kept all the stereochemistry around this first carbon the same, and this was the carbon with the chlorine in it. And if you look at this particular carbon, I can still label this as R because none of the stereochemistry changed in this molecule. So if I look there, you'll see hydrogen, chlorine, and methyl. You look there, hydrogen, chlorine, methyl. Nothing has changed. That's R, and this is also R. If you look at this particular structure, I've switched the hydrogen and hydroxy around. So here, I've switched the hydrogen and hydroxy around. So what was R is now S. So this particular molecule that I've labeled C is very different from this molecule. And if I look at models where I've built both, you can see that in this model I have this chloro group pointing toward me, the chloro group pointing toward me. However, the hydroxy group now is pointing away from me around this carbon, and the hydroxy group is pointing toward me in this carbon. You can see it very nicely with this particular molecule. So now I have 1, 2, 3 molecules. This and this. These two are mirror images, they are enantiomers, and this one and this one are not mirror images because they only differ in the stereochemistry of one carbon. We call these two diastereomers. So these two molecules A and C are diastereomers of each other, and so is this and this. B and C are also diastereomers because they also differ around one carbon. If I take this molecule and I rotate it such that I have the hydrogen, the methyl group there, and we have the methyl group here, and here you can see although around this chiral center everything is the same, now I'm pointing the chloro group away from me here when the chloro group is toward me in this particular molecule. So it's also different from here. I'm just going to put this back into the mirror image of the first one so we can see the next step. In the next step, what I'm going to do is take this molecule C and get an enantiomer of C by putting it in front of a mirror and getting a mirror image. And you can see that I've inverted all the stereochemistry, all the stereochemical centers. So what was R is now S. I'm looking at the carbon around the chlorine. What was R is now S, and what was S is now R. That's the carbon with the hydroxy group. There's the carbon with the hydroxy group. So by putting it in the mirror, I've changed all the stereochemical centers in the molecule. And if I look at a molecule of this, I'll take the carbon with the hydroxy group, and you can see that if I take that particular molecule and what I've drawn first, you can see that both of these are mirror images of each other, right? And if I look very carefully, you can see that the hydroxy group that I had here, I'll just show you, there's the hydroxy groups that I have here, and both these hydroxy groups here and here are pointing away from me into the mirror. Both these chloro groups are pointing toward me, and I have the methyl groups there, and there's a methyl group here and here. So these two that I've drawn later on are also enantiomers of each other, which means that both C and D are enantiomers, and A and B are enantiomers. However, if I look at all the different molecules together, you'll see that I now have 4 different molecules. I have a 2R, 3R in this first one. And if I look at the second one, I have a 2S, 3S. You can probably get a glimpse of here. Trying to focus. There you go. And then a 2S3R, that you see here. And finally, in this last one, when we focus, you can see that this is a 2R3S. And the numbers 2 and 3 refer to my carbon atoms 2 and 3 in this molecule. So we look at the carbon with the hydroxy and then put the stereochemistry in it. So it's 2R, 3R because the carbon with the hydroxy is R, then the carbon with the chlorine is also R. So that's 2R, 3R. Likewise here, again you look at the carbon with the hydroxy first, it's S, and then the carbon with the chlorine is S, so 2S, 3S. And if I go down, the carbon with the hydroxy here is now S, so this will be 2S because that's carbon number 2. You can probably see it now. 2S3R, carbon with the hydroxy S, and carbon with the chlorine R, and finally the carbon with the hydroxy R, so 2R, and the chloro S, 3S. So now I have 4 molecules by having 2 chiral centers in my molecule, and each of those molecules are different, and you would also find that the stereochemistry around each of the carbon centers can change. And what you would find is that if I have 2 molecules which are enantiomers, at each of the carbon atoms the stereochemistry changes at both the carbon atoms. However, if I have 2 chiral centers where the stereochemistry only changes in one particular carbon atom, you see here I have RR and only one particular carbon atom are changed, then those 2 molecules would now be diastereomers of each other.